Second talk this morning by Yasuhiko Sato from Kyushu University, and he will speak about KMS-bundles of the Jiangsu algebra for multi-parameter automorphism groups.
Well, thank you for introduction, and thank you for giving me this opportunity to present my research. Especially, thank you for organizers allowing me to give my talk. Today, I'd like to explain about my recent developments in my research for KMS data with multi-parameter automorphism group. This work based on our previous work, primarily in a joint work with George Elliott and Klaus Thompson, as well as a technique in a joint work with Hiro Matsui. In those works, roughly speaking, we can realize any possible KMS bundle on the Jiangsu algebra, KMS structure on the Jiangsu algebra. In other words, we can construct a one-parameter automorphism group that is an R action on the Jiangsu algebra, which realizes a KMS bundle, given KMS bundle. While I will skip the precise definition of KMS bundle here, but that can be described as a bundle of simplexes of KMS status with parameters on the real line. So, as you know, zero KMS state means a treasure state. For this reason, the condition of singleton fiber at zero is a necessary condition for a C-star algebra with a unique treasure state, like at the Jiangsu algebra. One of the key motivations of this research is its applications to the problem of operator algebras. We can use these results to construct uncountably many counterexamples to the Howard-Sakai conjecture. This famous conjecture proposed that every strongly continuous one-parameter automorphism groups of on a UHF algebra is approximately inner. Here, strongly continuous means just point-wisely non-continuous in common sense. But you know, this conjecture turns out to be false. The idea of this counterexample is that any approximately inner flow, approximately inner one-parameter automorphism group admits a KMS state at any parameter. So if we construct a gap on KMS structure, gap means the interval no KMS state exists, then that can be a counterexample. By using this, we can construct uncountably many such gapped KMS structures on the C-star algebra. Then that can be an example of non-approximately inner automorphism groups. You know that the algebra is absorbed in any UHF algebra and irrational rotation algebra tensor, then it is enough to consider that just algebra. In my talk today, I'd like to explain further generalization of this research to multi-parameter automorphism groups. Compared with the previous slide, the difference is just this one, from the real line to the hyperplane R to N. I'd like to refer this as multi-parameter automorphism groups. This generalization looks straightforward, but this led us a deep study of operator algebras, I believe. The result is conceptually simple, I think, but the proof is relies on a deep study of operator algebras. Well, to outline the proof, let me explain about the two significant obstructions we encounter in the proof. First, we should take care about non-simple C-star algebra in the proof. Secondly, we also should consider about non-amiable group actions. Very roughly speaking, in the proof, the Jiangsu algebra will be constructed as a cross product by the free group action known to be non-amiable. I will explain this rationally AF algebra later, but this A should be non-simple, corresponds to unbounded KMS vector. In the remaining time, I will explain the reason why we need to consider about non-simple system algebras and non-analytical group actions in the proof, and the way to avoid such obstructions. Well, the reason of non-simplicity is derived from the following property known as the least interpolation property. An ordered Abelian group is said to have the least interpolation property if for four elements Gi and Hj, such that each Gi less than Hj, there exists an element A between the upper bound of Gi and the lower bound of Hj, like this. A typical example of the least interpolation property group is the group of polynomials like this on a closed set. Here, S indicates the parameter of KMS status, but let me skip it. Under this assumption, equipping G the strict ordering, it is not so hard to see that G has the least interpolation property if and only if S is bounded. The direction from boundedness to the least interpolation property group is just the Stone-Weierstrass theorem, but the converse direction is not so hard. At that time, the situation is not so complicated because this G can be a simple dimension group. On the other hand, our result requires a specific ordered Abelian group like a Laurent polynomial. Precisely, this example is slightly different from the original one in my proof, but the idea is very close to the second example. Here, equipping with the strict ordering, this G has the least interpolation property if and only if S is semi-bounded. Semi-bounded means just existence of lower bound or upper bound. Then S can be unbounded set here. But the problem is if S is bounded, in that case, S can be a non-simple ordered Abelian group, non-simple dimension group. So for this reason, if we want to realize unbounded KMS spectra like as S, then we need to take care about the non-simple ordered Abelian group. It turns out correspond to non-simple system algebra. That's the reason we should take care about non-simple system algebras in the proof of our main result today. So, well, this is the reason for non-simplicity. Next, let me move on the non-amenability. Non-amenability is rather easier to understand, I think. In our previous talk, for one parameter automorphism group to realize KMS spectrum, KMS structure, one can obtain an ordered Abelian group G and action on it. I will skip the construction and the detail, but G and sigma can be realized by depending on the KMS structure. And so first we can realize this G and sigma as a certain system algebra. As I said, rationally AF, I will explain rationally AF algebras later, but this alpha is a shift of this sigma. Then the Jones algebra for one parameter automorphism groups, the Jones algebra can be constructed as the cross product by the integer group like this. Very, very roughly speaking, KMS status on the Jones algebra correspond to eigentraces of AG, a kind of eigentraces of AG. And for this reason, in the case of one parameter automorphism group, it is enough to consider amenable to B action. But for multi-parameter automorphism groups, to adapt a similar strategy, we should take care about more complicated situations. One can also construct a dimension group D and an action of D to N corresponding to R to N, naturally considering we need to take care about D to N. But the obstruction happens in the lifting of this D to N. Of course, although each individual automorphism can be lifted on a C-star algebra, on a certain C-star algebra, but we lack a method to make commute each other. Then for this reason, we cannot lift this action to a C-star algebra straightforward. Then we should take care about the free group action on a C-star algebra. That's the reason we should take care about the non-amenable group action by the free group. But from the construction of the C-star algebra of rational AF algebra, we can avoid the non-amenability of this one. This action will be amenable action on this C-star algebra AG. So these are obstructions of non-simplicity and non-amenability. Let me summarize. To construct unbounded KMS vector, we need to take care about non-simple C-star algebras derived from the least interpolation property. And for the issue of lifting problem, we should take care about non-amenable group actions. Well, in the next two slides, I will explain the way to avoid these obstructions. First, let me consider the issue of non-simplicity. The celebrated classification theorem for AF algebras, as you know, does not require simplicity at all. I think all of you are very familiar with the classification theorem for AF algebra very well, rather than I am. But for double checking, let me recall the classification theorem for AF algebras. In the early stage of the classification theorem, for Bradley and George Eliot classified AF algebras by using the Bradley diagram and K0 groups, as you know. But at that time, they didn't assume simplicity at all. AF algebras in the classification theorem, even for non-simple settings, correspond to non-simple ordered abelian groups. Our class of rationally AF algebras can be regarded as a natural extension of AF algebras. For this reason, we can classify the class of rationally AF algebras here. Roughly speaking, rationally AF algebra means C-star algebra becomes approximately finite dimensional after tensorial UHF algebra. We refer such C-star algebra as rationally AF algebra. Very straightforward definition, I think. But to classify rationally AF algebras, we introduce a special class of ordered abelian groups called rationally dimension groups. The setting parallels with the dimension groups, but the difference is just tensoring UHF algebras, K0 group of UHF algebras here. But the key technical part in this setting is for non-simple ordered abelian groups. Technical part is we need to take care of two distinct UHF algebras here, not just one UHF algebra. To relatively prime UHF algebras, we define such rationally dimensional groups. Well, even in the presence of non-simplicity, we can classify rationally AF algebras. As you know, Wilhelm Winter introduced a powerful classification method called localization technique, modeling the construction of the Yasuhiko algebra. By using this method, we can classify rationally AF algebras because this class is very close to AF algebras. Very roughly speaking, that's the way to avoid non-simplicity in our proof. The class of rationally AF algebras can be classified by just K0 groups of rationally dimension groups here. Next, let me explain the issue of non-amenability here. This problem was I think, addressed in a classical work by Bradley, Elliott, and Kishimoto in a similar context to realize a KMS bundle on a certain amenable C-star algebra. even for non-amenable group G, if we construct a shift action, natural shift action in the high centrality, this action can be amenable action. Here, G of A is not the dance algebra. Sorry, this is the central sequence algebra, and here I forgot the fullness meaning of this G0G, but certain fullness, assuming the certain fullness and constructing such shift action on a high centrality, we can see that the action can be amenable action in the sense of anathema and their logic. That's the reason we don't need to assume amenability in our proof. Because in our construction of rationally AF algebras, it might be straightforward to construct such natural action. Because this is the reason why amenability is very roughly speaking. The shift action of this alpha, the cross product of this shift action can be the compact operator algebra. Then by using the high centrality and the approximate diagonal of this one, we can obtain a kind of amenable group action and approximate diagonal of this C-star algebra. Then for this reason, in our construction of the Jiangsu algebra, we see that the reduced group C-star algebra is not clear. We can apply the classification theorem for this C-star algebra. Well, finally, let me comment my result. Today, the result of my talk is for simple C-star algebra and for amenable group action of R to N. But the proof requires a technique of non-amenability and non-simplicity for the algebras. A little bit earlier, I think, but that is all my presentation. Sorry.
In your definition of rationally AF, I didn't quite understand, is the Jiangsu algebra rationally AF?
Yes, the Jiangsu algebra is rationally AF.
Because in this definition, it looks like you're only tensoring with the finite. I mean,
yeah,
the
but
specific K and L.
Specific K, but this is equivalent to any UHF algebra. By tensoring any UHF algebra is equivalent.
Also, this is the definition for rational dimension group, right? For rationally.
But rationally AF algebra is the same thing for certain two relatively prime UHF algebras tensoring that it becomes an AF algebra. Then we say rationally AF or some rationally AF algebra. Then in the setting of simple shift algebra, one UHF algebra is enough, I think. But for non-simple shift algebra, we need to take care about two relatively prime UHF algebras. That's the difference. In the past, Huaxinlin and Tanyu also introduced a similar notion. I forgot the name, but at that time they considered about simple shift algebra. Then they have introduced saying very similar notion for a kind of rationally least group or something. But this definition is for by using two relatively prime supernatural numbers.
Nine. Yeah, sure. Ask another question. For these lifting these actions, you said the problem is that you can't make the lifts commute.
Yeah. Then we don't need. I mean, we don't need the free.
Yes, I understand. But if you just took a tensor product of Z with itself and do it on every tensor factor, then why is that not enough?
Not enough, I think. If we consider the tensor product, the KMS structure will be broken in my version. So we want to realize KMS structure for a simple system algebra,
Yes.
but that cannot be arbitrary. KMS structure cannot be decomposed into tensor product, I think. Then we cannot use such technical results in my version.
Can you say something about the action of R to the n? Is it just a dual?
Dual, yes,
Dual action.
dual of D to N.
Could you replace maybe with a single action that is wrapped around?
Yeah, just forward action.
That's a torus action, but there's a possibility of angling an action of R so that it's dense in the torus. So I wonder if you could do this theorem for a single parameter action that is somehow wrapping itself around the torus.
Right. No, well. Well, if is we can argue and at the conjugate homomorphism to R from R to T or the torus. Then
Okay, so those betas are joint. Okay, so that's what I was wondering. That's exactly. Yeah. Thank you.
Any further questions? If that's not the case, then it's going to speak again.